Okay, hello everyone and welcome back to the third session of this workshop series in data-driven linear algebra. And so this session is all about the application of the singular value decomposition. We've learned a lot about it in the last two sessions, about the theory and how we would compute it in practice. And now we're going to have a look at using Python to compute it in a much more simple way, actually apply that to solving a variety of different problems. And so all the coding today is going to be in Python. A knowledge of Python is not really important. All the code is going to be commented and I'll walk through exactly what the different bits are doing. And then hopefully we'll get some translations up in other languages over the next few weeks so you can have a look in whatever language you're the most familiar with. So I have this notebook here. I haven't released it just yet. I think it's better just to follow along with what's going on rather than having the code for yourself. But I'm going to get that released later today so you can have a go at running it. This exists in Google Colab. It is an online cloud editor which allows you to run Python code without needing to install anything. So it's a very easy way to get going without having to set up Python and faff around with that. So with that, let's start working on the first example. So we start by doing some setup code here. Your Python comes with these things called packages. Those give us extra functionality on top of the base language. So we import a few of these packages and a few more from what's called the SciPy family of packages. So the first example we're going to look at is image compression. So taking an image represented as a matrix and trying to use the SVD to represent it in a lower rank format. And that's going to correspond to representing it using less storage. So compressing the image down so we could transfer it on the web, say, using less memory. And so I want to start by offering some motivation as to why image compression should even be possible. Because, there's no guarantee that we should be able to compress an image. We have the image there. Why should we be able to represent it in a smaller form without losing that much information? And kind of the motivation that I think about, kind of why this works, is I want you to imagine the space of all possible images. So imagine we have, a 1 megapixel image. So that's 1,000 by 1,000, say. And each of those pixels can have, let's say we have an 8-bit image. They can each have 256 different values. Well, then the number of combinations of images we could possibly have, there's 256 possibilities for the first pixel, 256 for the next, and there's 1,000,000 pixels. So that's 256 to the power of 1,000,000. Now that is an absolutely gigantic number. If we compare that to maybe 10 to the power of 70, that's around the number of atoms in the observable universe. And we're absolutely, we're nowhere near that in orders of magnitude. We're way, way bigger. It's a number that, you can't even reasonably contemplate. So that's how many possible images there are, but the amount of images we care about in reality is a lot smaller. And the ones we care about tend to have certain patterns. Like we don't care about random images. There are certain trends and patterns in our images that actually mean something to humans. And so for that reason, we should be able to express a small pocket of this whole image space in a more efficient way. And so the SVD allows us to pick out those kind of more important patterns and features and ignore just the general noise that might be on the image, say just from random fluctuations in a camera sensor, say. So that's what this example is all about. And we're going to take an image of a cat. But you can rerun this with any image you like. It should be robust enough just to change this URL here to any image, and you'll be able to run it with your own image. And so the two parameters here are URL to an image, and then we're going to create low rank approximations of this image. Here I pick 6 ranks to use: 1, 5, 10, 20, 40, and 80. You could play around with that when you use it. So we're going to start by loading in this image. The image looks something like this, but in color. So originally this image is in color, and you can think of this as a tensor. And so a tensor is kind of like a matrix, but with more than 2 dimensions. So imagine this image was in color. Then you can think of it as being a matrix, or 3 matrices stacked on top of each other. So the first one's going to be the red channel, how much red there is in each pixel, then green, and then blue. So it's a matrix of this size, but then you stack 3 of those on top of each other. And so if we load this image in, so we make a request to the URL, and then load that into a tensor that we call T. If we print out the shape of this, we see it's 546 pixels by 970, and there's 3 color channels there. So this is not a matrix, there's 3 dimensions here, it is a tensor. And the singular value decomposition is not meant for handling these multi-dimensional arrays. And so what we're going to want to do is collapse this down to a single matrix with a single channel. And so we do this here by taking the final channel, which is, we use -1 to represent the last channel, which is the color one, and we take the mean over that. So if we had red pixels of strength 10, green of strength 50, and blue of strength 90, then the average of those would be 50. And this will return us a grayscale image, so just kind of a black and white image. And so now this has a shape of the same dimensions, but with only one channel. We've flattened that down. And we're also going to look at what the storage size of this is, and it's about 4,000 kilobytes, so 4 megabytes. A fairly big image, not much compression has taken place already. And we're also going to keep track of the aspect ratio. That will just be handy when we're doing plotting. Doesn't really matter for the actual computation of the SVD. So the original image looks something like this. We can plot it in grey. Here's a picture of a cat. And, you know, there's a lot of complexity in this image, a lot of kind of, detail in the cat's whiskers and kind of all its hair, and some nice kind of fuzziness around the side here. So it's quite a complicated image, but hopefully we'll be able to reduce it down into a simpler representation without losing too much of that information. Okay. It's worth noting here that in this example, we're storing the entire image as a matrix. So we saw in some of the examples in session 1 and session 2, this idea of storing a matrix where every column is an image flattened out into a single vector. Then we had multiple images. And we'll see that again when we get to the next example, but this one is focused entirely around having the whole image represented as one matrix. And so rather than trying to pick out kind of a low-level palette for making all the images, we're picking out a palette for the column space, and then we're going to combine those together by taking different mixtures for each column here. Okay, so let's do the singular value decomposition. Very easy to do with Python, very fast to do as well. So actually, let's make sure we're running all these. So let's run all the ones above here. Okay, so that gives us the image there loaded in from a URL. And now let's compute the SVD. So we have U, S, and VT. I use S instead of sigma because sigma is quite a difficult character to type out in a Encoder editor. And we do this by using linearalgebra.svd on our matrix X. And we use here full matrices equals false, and this gives us the economy SVD. So this is the kind of the reduced form where S is a square matrix, but in this case, V is no longer orthogonal. So we compute the SVD, and then we get these dimensions here. It's worth mentioning, because there might be some confusion here, that when we did the economy SVD before, it ended up being U that became rectangular and not orthogonal. And that was because the number of rows in our matrix was typically bigger than the number of columns. But in this case, we can see the number of rows is smaller than the number of columns. So actually, it's the V matrix that gets truncated, but the idea is the same. So having a look at the dimensions of these, we have U being a square matrix. These represent our columns, or kind of like a basis for our column space. S gives the weight of those different columns. And then the V matrix tells us how to combine these columns back together to form the original image that we had there. Okay, yes, so don't be put off by these being swapped around. It's just a fact that we had a different dimension of image or different aspect ratio than we're used to. So let's look at the storage size for this. So when we look at all those matrices together, U, S, and V transpose, their total storage size is 6,000 kilobytes or 6 megabytes. Now that's actually more than we had originally. Originally we had 4 megabytes. So that's not great, and it's kind of worth noting that, you know, the SVD only saves space when we do a truncation of it. So the SVD itself, kind of the untruncated full version, is an inefficient way of storing the data. Because, you know, if we can store the data by itself or store it in this complicated format, it's unsurprising that the complicated format is going to take some more space. So we had that down here. But the idea is now we can truncate it at a certain rank R, and that will save us space. So let's plot out the singular values first. So 2 plots here. The first one giving the singular values, so the values in this S matrix, and we take the logarithms of those, and we see we have this absolutely lovely elbow here. So an elbow that kind of flatly decreases for the rest of the plot. So this is like a really good plot. This is very promising. It suggests that at around maybe, I don't know, 50, 60 singular values, we actually get a pretty good approximation and don't have to worry so much about including those latter terms. We can see the same thing here. When we look at the percentage of variance explained, around about 60, we're about 70% of variance explained. And then after there, it takes, quite a few more a few more one-rank matrices to be added to actually explain the whole of that variance there. So this is a very good plot, and it's a promising sign that the SVD was a good thing to do. And so let's ask the question of how much memory is being taken up by the truncated version of our SVD. So the original matrix is, or has dimensions of m by n. So we're going to need, if you're not seeing this big O notation, it means kind of an order of magnitude. So about m times m values in storage to represent the matrix. So this is not great if we, if we increase both m and n at the same time, so scale our image, this is going to grow quadratically. So if we make m and n twice as big, so we scale our image by a factor of 2, we're going to need 4 times the storage. So it's growing kind of out of proportion to how big we make the image. That's not great. But if you do a rank R approximation, this U matrix is going to have dimensions m by R, and sigma is going to have just R entries, and V transpose is going to have R by n. So those are kind of the individual ones, the order of magnitudes of those, and then we just add those all together, the total amount of memory usage, and we'll find that we have MR, NR, then we ignore the R because these MRs and NRs kind of dominate the storage size, and we end up with something where it's M plus N times the rank here. So if we fix our rank approximation, and now say we double the size of the image, rather than kind of quadrupling as we had before, now we only double the amount of storage that we need. So this is a far more efficient representation of our data. And so actually plotting what this storage capacity looks like, you can see that with our original data we had this many entries, and then when we have the full rank approximation of the SVD, it is worse, but then it decreases linearly as we decrease the number of ranks we're using in our approximation. And so once we're below 350, 360 say, it becomes a more efficient representation. And when we're in these very small things, we're saving quite a big fraction of our storage. So now the important question is, how good do these reconstructions look when we use a low rank approximation? And that's what this addresses at the bottom here. So we're going to take our those ranks we defined above. So let's just have a quick look at those. So the ranks were 1, 5, 10, 20, 40, and 80. And we're going to kind of construct the low rank representations using the SVD. So we run through each of those ranks, then we create an approximate version using only the first R rows and columns of U, S, and V. And then we're going to keep track of how much storage is saved and how much variance we've explained of the original image. So we'll start off with a rank 1 approximation. This is using just 0.3%, so a 300 times saving in storage, but we don't really have that great an image coming out. But even that said, you'd be surprised that 20% of the variance of the image is captured here. Like the most important elements, which is that there's something in the middle and darkness in the background, that is captured just in this one rank representation. So we've done a very good job of capturing as much information as possible. And in fact, we know it's the best because of the Eckert-Young theorem, using just using a rank 1 matrix. And now as we start to add more ranks to our approximation, the amount of storage that we use increases. We now have 1.4% storage, but the variance goes up as well. We're now explaining 35% of the variance. And we can start to see, maybe there's something animal-like, but it's hard to tell exactly what. By rank 10, we can tell, yeah, that's a cat. It looks very rough around the edges, but we can tell there is a cat there. And we're still only using 3% of the original storage. Up to 20, and that's becoming pretty good. Some artifacts, especially around the edges here, where there's kind of this fuzzy blurriness. That's 50% of the variance explained, using only 6% of the original storage. And we carry on with 40, and then finally to 80. And by 80, we have a pretty good approximation that this looks almost like the original. Maybe it's not as sharp around the edges here. We've represented about 80% of the original variance, but using only about a fifth of the storage. So a really great job there. So the final thing we're going to look at in this example is optimal truncation. So we saw the paper by Gavish and Donahoe, which gave an optimal way of truncating our matrix or our SVD based on the fact that our matrix was composed of some true signal and some noise. And so we're going to use this formula. If you remember from last session, it was some kind of correction factor based on the aspect ratio, so some omega of the aspect ratio times by the median singular value. Now this omega is very difficult to calculate. Actually, there's no analytic representation. You have to use a numerical approximation. And so I've just written out here this approximation taken from the paper, kind of a third order approximation, which will do a good enough job for our circumstance. So we create this threshold tau by timesing this omega of the aspect ratio by the median singular value. And then we cut off all singular values that are larger than this threshold here. And that gives us a rank of 95. So 95 is in some sense the optimal truncation for this problem. As this gives us this image here, you're very crisp. We pretty much have everything in the original image, but now with 27% of the original storage. So an absolutely incredible job done there. Okay, so we're now going to look onto an example of dimensionality reduction. And this is very similar to principal component analysis. I'm not going to get into how the SVD and PCA are related, just because I don't want to have to explain PCA to anyone that doesn't have a statistical background. But if you are familiar with PCA, then if you just search for computing PCA using the SVD, you'll see that they're intrinsically linked and actually kind of represent the same thing, just using different names. So the idea is in this, we're going to look at performing dimensionality reduction. So taking a big data set and representing it in a lower dimensional space. And we're going to do this on a data set called the Yale B Faces data set. So this is a data set of 2,410 images, which are 192 by 168 pixels, of 10 different human subjects taken in a wide variety of poses and illumination conditions. And the way they take these images is they sit someone down in a certain pose, and they sit inside this kind of geodesic dome with loads of different lights placed around them. And then all the lights flash one at a time to get different lighting conditions and pictures are taken. So they're very similar facial expressions, but with different lighting, and then they repeat that for about 9 different poses. So setting this up, we again pick out our ranks and just jot down what those image dimensions are going to be. So we load in these faces. I've kind of put these into a NumPy pickle file, which I'll put on GitHub for you to use for yourself. We load those in and we see it has 32,256. That is, so that's the number of rows, and that number comes from the product of these two numbers here. So each of these images is represented as a long column vector. So whereas before we had the image represented as a matrix, here we flatten it out into a single vector, and those vectors make up the columns. And there are 2,410 of those columns, one for each image. So that's the matrix that we're dealing with. Let's start off by just printing out a random selection of 36 of those images. So we're going to make a collage of 36 images, loop through, and randomly pick out one of these 2,410 images. And then we make a collage by just taking those across, copying them across, and then printing out that image. So it looks something like this here. So various different faces, different poses, all quite a neutral facial expression, with different lighting conditions as well. And the important thing is these have all been aligned so that the eyes and noses and mouths are in roughly the same space. Space. And I'll talk about at the end of the session how this is a limitation of the SVD, that it requires that these faces have to be aligned properly, or it doesn't really work or make any sense to do the SVD. But in this case, they've been aligned for us, so everything's looking pretty good. And what we're going to do, we're going to hold back a single face. So we're going to build the SVD based on this data, but only for 2,409 of these images. We're going to reserve one to use as kind of a test of how well the SVD works on new data. So we're going to take back this just one particular image, 253. We're going to delete that from the original matrix X, and then set that to be our holdback image that we're going to use for later. And so from that, the first thing we're going to do is center our data. So we're going to use this mu variable to represent the average face. And we compute that by taking all of these columns, kind of adding them all up, and then dividing over the rows. So we're basically calculating what the average face looks like. We can actually have a quick look at what that average face might look like. So if we just do plot.im show mu, I think we're going to have to reshape it into what size we're going to want there, n and m, and then just transpose it so it prints out the right way. If we do that, we have to run all the code above first. So this is going to give us what the average face in the dataset looks like. And the reason we're doing this is that if we're building a palette of faces, what we really want to capture, or what's more informative to capture, is how different faces differ from a typical face. Starting from that center point gives us a much more informative SVD than starting from nothing, like a black image, and kind of building up the faces from there. And so that's what we're going to do in this scenario. It's it's not cheating. We just redefine where our 0 is to give us a more informative answer. So this is just taking a second. We're computing the SVD here, and we're not computing the SVD of x, but x after taking away kind of a repeated version of this this mean matrix. So basically, we're centering all of these faces around the average face. So rather than doing the SVD of the faces, we're doing the SVD of how these faces differ from a typical face. And so then our eigenfaces are going to represent kind of a palette for kind of what components we can add to show how people differ from a typical face. And so looking at the average face, why didn't it like that? That should have been on the outside. Okay, this is what the average face looks like. Let's do that with a grayscale color map. So it's a bit creepy, but this is what the average face looks like. And so we're going to have that as our base, kind of as our origin, and then we're going to add and subtract things from that to get the other faces. So you computed the SVD, the economy SVD as before. So we're now going to have a look at what are called our eigenfaces. So basically this is the columns of U, which kind of give us a basis for constructing the actual faces from this average face. And so these are weighted or kind of ranked by these singular values. So we have a most important eigenface that's going to capture the most important difference of the faces. And then we're going to have less and less important ones. And so these look something like this here. And so this is absolute nightmare fuel. But we can see here, these are kind of, I guess, components we can add to the average face. And the importance of these components are given by these weights here. These are the singular values. So this is the most important here. I guess this kind of represents, it's probably kind of a lighting change. So lighting coming from the bottom left. This one here is kind of lighting from the right. And you want to see, most of these are going to represent different lighting conditions because those are going to make a bigger difference than the actual facial structures. But we'll see as we get to some of the later ones here. Kind of this one introduces maybe some more kind of characteristics of an Asian face. So that's maybe hair and eye and eyebrows that are more typical of that sort of ethnic background. And we'll see that when we reconstruct later that this is actually quite an important eigenface. So these, yeah, very creepy, but it's also a very fascinating idea that these are the most important aspects of what makes up these images here. And so now we're going to do something very clever. We're going to take that holdback image that we kept before, and we're going to map it through this this transformation U. So basically what we're going to do, we're going to represent it in a low rank form. And so this is kind of a way of compressing down that image. So we represent it using just the first few ranks of our data. So maybe we try and represent this holdback image using just the first 20 ranks of, or the first 20 left singular vectors of the singular value decomposition. And what we can do from that is then reconstruct it back into the original image. We would hope that in most cases, the reconstruction will be fairly accurate, even with a few ranks. And so that's what this is going to look like here. So we're going to start by plotting the original face. Looks something like this here. And then what we're going to do, we're going to do a one rank approximation. So take this face and represent it using only this eigenface here. And we're doing this using the scale versions again, so centering them around the average face. So using just that one, we can reconstruct this image kind of after mapping it through that one rank space. And we can do a similar thing as we add more ranks. We'll see the approximation gets better. And once we get past the 9th rank, so the 9th rank contained this eigenface, which had kind of this type of hair and these types of eyes, we see that the approximation becomes a lot better. And actually, we're pretty spot on. Like, we don't have the actual kind of composition of the pores and all those kind of things, but the general face is there. And that really is quite amazing because the SVD was not computed using this face. So it has no knowledge of this face. And yet using its basis of 20 most informative features about faces, it was able to construct a pretty good representation of what this original thing looked like. As we go up to 100, 400 and 1000, we pretty much have the original image back, despite it never seeing this before. So we can see that this palette is not just representative of the images it saw, but of all images that have this sort of structure. And so this would be useful for compression. Because for example, if we looked at this rank 100 approximation, I could take this original image, a lot of data, and reduce it to the 100 rank representation. And I could pass you over that reduction. That's going to have a lot less. It's just going to be the coefficients that you use to reconstruct it. So a really low rank representation of this, and then all you would need to have is the same U, sigma, and V that I have, and you could reconstruct this image. So I never needed to send you the original image. I could just send you this reduced version, and you could reconstruct the original one. So it's really quite beautiful idea. And in practice, it works really effectively. So there's one more example that I'm going to add after this session based on regression. I didn't want to include it in this session because it's a bit statistically heavy. But when I send out this notebook later, I will have added this so you can have a look at it for yourself. So that's just a reason to come back and look at it later to see an example of a more statistical view of the SVD. Okay. And so we're now going to look at some other ideas. That's kind of the examples. Talk about some wider applications of the SVD and some limitations of the SVD. But before we get to that, we're going to have just a short 1 minute break, just to let things settle in. Then we'll join back again to talk a bit more about what else we can do with the SVD and some other methods we can use when we reach its limitations. So I'll see you back in a moment. Okay. Oh, didn't realise that we had started again. Sorry about that. So now we're going to talk about some actual kind of more complicated applications, some wider applications of the SVD. And so the first thing we're going to look at is how the SVD is used for search and recommendation algorithms. And we're going to, in particular, look at the Netflix prize. So the Netflix prize was a competition ran about a decade ago now, in which $1 million was offered to whatever team could devise the best algorithm for building a recommendation system for Netflix. So the idea is this is all based on a matrix. We have a matrix looking something like this. It's a really massive matrix where each column represents a certain person. I guess let's use n for this, as we've done conventionally. And each row represents a certain film. So these are people, and each row is a film. And what a single value represents is a person's rating for a certain film, say out of 5. Okay, and so this is a very sparse matrix. It's unlikely that we're going to have for every single person in every single film what their rating was. In fact, for a certain person, we might only have 20 or 30 ratings, and for every person there's going to be a different collection of films that we have ratings for. And so the goal of the Netflix Prize is to fill in those gaps, to kind of take those missing values and give an estimate for what they might be, and use that to kind of predict whether a person would like a film, and then use that to recommend them films that they do in fact like. And so one way we can kind of think about this is, suppose, for example, suppose for a moment that this was a complete matrix. Although we would like to believe that we all have very unique tastes and are very unique people, in fact there's probably some kind of low rank representation of this matrix kind of captured by the dominant correlations. And so if we had the whole matrix, we could compute an SVD, and that would give us a lot of the general trends. Okay, it seemed to have lost connection to the screen. I'll be back in one moment when that's working again. Okay, we should be back again now. So the idea is that we want to kind of represent this matrix in a low-dimensional form. And this is going to capture the general trends of people. So we're basically going to calculate the eigentastes of different people and kind of, the sorts of films that they like to watch. So a certain eigentaste might be people that watch comedy films or people that watch action films. And then there might be even more kind of specific things that people that watch action films involving Arnold Schwarzenegger. And the idea should be that everyone's film preferences can be roughly made up by combinations of these eigentastes. And so if we had this low rank representation, we could be able to kind of figure out patterns. If you liked, a certain comedy film, and I like that same film and another comedy film, well then it might be the case that you would also like that second comedy film. And so if we had an SVD, we could kind of build those up very simply. But the problem is we're missing data. And so, how can we handle this? And the solution is using a thing called the robust SVD, or the robust principal component analysis. This is not something I'm going to get into. It's a bit of a more complicated topic, but it's kind of a variant of the SVD that is robust to these missing values. And we kind of work under the assumption that this low rank representation exists. We try and find it, they can use that to reconstruct the original matrix without the missing values. So this is robust to these missing values. It's also robust to if someone was deliberately putting in invalid recommendations. So if someone was trying to cause mischief and deliberately putting in false ratings, it would be able to kind of remove that bias and give an accurate reflection of the actual ratings. And so that's the application for kind of recommendation systems, and similar things are used in search systems like in Google. So that's kind of the wider applications. But now we're going to talk about the limitations of the SVD. And so we're going to start by talking about invariances. And the reason we're talking about this is that the SVD is not very tolerant or robust to invariances. And there's two types of invariances we're going to look at, translation and rotational. And so let's imagine we're back in this eigenface setting where we have people's faces. And in the example we had before, people's faces were aligned so their eyes and mouths were roughly in the same place. But what if we have a scenario when the faces are not aligned? That we have two different faces in different places on the image. Well, this is going to cause us problems because the SVD is kind of associated with this matrix xt, so x transpose of x, which is the correlation matrix, the correlations between this matrix x. And we can think of this, as a matrix of the individual correlations between the different rows. And so there's the correlations between the rows and itself. And so this is only going to make sense if we have the matrix properly aligned. Because we need to be comparing like for like. This works because if we have the eyes in the same places for both matrices, then one of the elements of x represents that pixel representing the eyes. And if both of those have the same value at the eye, they'll be times together and we'll get a very large inner product for that pixel. But if these aren't aligned, then we're comparing completely different values. Here, where the eye was in this image, we're comparing against kind of background here. And so this isn't going to accurately represent the correlations in our matrix. Instead, this is going to be absolute garbage and will tell us nothing. And so the SVD is not suitable for these sorts of problems where we need translational invariance. So translational meaning, we move this by translating it to a different position. So a solution for this is using something called a convolutional neural network. And so this is a type of neural network that is very good for handling translational invariance. It works by taking this thing called kernel, which is like a grid of weights that represent a certain mixture of pixels, and scanning it across the image to build up a new representation. And so a method like that would be translationally invariant, and so would be a good replacement for the SVD in this sort of scenario. Another approach would be simply to use some sort of pre-processing step to maybe figure out where the eyes are, where the mouth is, and then crop down the image like we had in the Yale dataset to center around those. So that's two alternatives. So another issue is that there was translational invariance, and the other type of invariance we're going to look at is rotational invariance. And this is to do with rotating an image. So you can imagine when we had that cat example before, imagine we're trying to take an image and represent it in a very low rank space. And so let's start with an image that looks something like this. So it is a white square with a black square in the middle. And so actually we can represent this very easily as we could take a column vector, which is just black in the middle, and a row vector, which is black in the middle. And then the product of these is going to give us this matrix that we had originally. So this has a rank 1 representation. It's very easy to collapse that down into a low-level representation. But what about a matrix like this? So an image of a diamond. And we could have obtained this by taking that original image and just rotating it. So really, to us humans, we can instantly go, well, these are the same image here. But to the SVD, these are very different images and have very different intrinsic ranks. In fact, this is going to have a really high rank. The rank is going to be actually equal to kind of how many pixels going across here we had. And so it could be the case that this is going to be a really difficult matrix to represent using the SVD. And we could do an approximation, but the approximations are not going to be as good as that square one. So that's another problem with the SVD. It's not rotationally invariant. And so we could again get around this by using some sort of pre-processing step to kind of align things rotationally. But really this is quite a difficult problem to solve. even when we're using things like convolutional neural networks, they can struggle with this sort of thing. So it is a tough problem. It's worth being aware that the SVD can stumble in these sorts of cases. Okay, and so the last thing I want to talk about is another flaw of the SVD, and that is that it's looking for kind of linear combinations. So I'm going to be very kind of vague talking about this, but the SVD is kind of based on these linear combinations, kind of breaking up your matrix into these, different columns times rows that then get added together in a linear way. And so this is no surprise. The SVD is a linear algebraic technique, and so we're dealing with this very simple representation. It's a powerful representation, but it has its limits. And I'm going to give kind of an analogy. It's not really related to the SVD, but kind of example of where linear correlations or linear patterns cannot accurately represent our data. So imagine for a second we have data that looks something like this. So this is kind of a regression case we're looking at here. Again, not related to the SVD, but it's a good motivating example. We could easily represent this trend with a straight line here. So this is our x and this is our y. What if our data looks something, actually let's put this in the middle, looks something like this. So x and y. And our data looks something like a circle here. So as humans, we can easily pick out what the pattern of this data is. But you can imagine that if we're a linear classifier, the best we can do is, I guess, something going straight through like that, because we're restricted to only linear solutions to the problem. And the same with that, the SVD is restricted to linear solutions to dimensionality reduction. Now, how could we get around this? Well, we could use a more complicated classifier, or some more complicated method, or another idea would be to transform it. So maybe what we could do is to plot the radius of the points against the angle of the points. And so we see here that there's these all have radius 1, and the angles kind of go between 0 and 2 pi. So now our data looks something like this. It seems to have frozen again. Hopefully that will come back in a moment. Let's see, hopefully that will reconnect. But the idea is that by transforming this data, we now have a much better representation that works well in a linear case. So we can see that there. And so this was a very kind of trivial example, but it kind of goes to show that even if we're trying to model a non-linear system with a linear classifier or sort of a linear method, there may be a transformation that can save us. But if not, we're going to have to look at some more complicated methods. And so one more complicated method that we could use is what is known as an autoencoder. And the idea of an autoencoder is that it kind of takes our images, say a face here and a face here, and it tries to kind of take these down to like a low-level representation, which we call a latent representation, and then builds them back up. And the idea is this latent representation is very minimal, very constrained. And so if you want to be able to reconstruct the images using this limited space, this latent space is going to have a lot of information about those images, capture the most important things. And so we can kind of generate this using a neural network, kind of training it on a lot of images and slowly building up the best latent space representation over time. And so that's kind of alternative to the SVD, a more powerful one. It's a bit more data hungry, but can capture these really complicated non-linear aspects of the data. So with that, I think that's all we have for today's session. So I'm going to post the notebook for today's session on the event page on Facebook later today. Then we'll add the regression example sometime over the weekend. So with that, thank you for sticking with this course. I appreciate there's been some very heavy parts of it, but hopefully this has kind of inspired you to learn more about the SVD and kind of appreciate that there's this very data-centric side of linear algebra not taught in university that's really important for kind of practical applications. So with that, thank you for coming, and I'll see you around.